All right, here's our goal. Linearize data and use slope of linearized data to solve for K. What are we talking about? We're talking about doing an energy lab here. So let's talk about what's going on. We've got a spring over here that is currently in its relaxed natural length state. And there's a little person that's going to be launched by the spring and is going to head across this blue line and across this blue line, and that's 18 meters. And this is considered a frictionless surface. So energy is being conserved by our system here. Our system consisting of the spring and the person being launched. And we've got a little timer that we can reset. You've got the mass down here, which you can increase or decrease. The spring constant, which you can increase or decrease. And little timer. So let's show you how this works. It says set Trevor. So we get zoomed in, and every time we pull back the spring, this is the relaxed position of the spring. If you click the pull back once, that's 0.2 meters, 0.4, 0.6, 0.8, 1.0 meters, etc., etc. And then if you hit fire Trevor, right, you would click start timer as soon as it crosses the blue line. And then when it crosses the second blue line, boom, 5.9 seconds. So basically it traveled 18 meters. I'm using my calculator here. 18 meters divided by 5.9 seconds gives me 3.05 meters per second. So that's my velocity for that experiment. So we can do these different launches, changing either the mass or the spring constant, and then study what happens as a result of that. How does the velocity change? Okay, so let's talk about the physics going on right now. So if we get into, okay, let's talk about energy. We have initial energy plus work equals final energy. And our system was defined, we're going to define it as the person in the spring. Okay, we don't have to worry about the Earth as part of our system. We only have horizontal motion, so we don't have any gravitational potential energy anyway. Now, because it's a frictionless surface, there is no external force doing work on our person as they slide across the ice, right? They're going to have gravitational force going down and a normal force going up, and that's it. Those are all the forces on the person as they slide across in a constant, with a constant velocity. These forces are perpendicular to the direction of motion, so they are not doing work. If you considered the formula FD cosine theta for calculating the work being done, theta would be equal to 90 degrees, and cosine of theta is cosine of 90 degrees is 0, right? Cosine of 90 is 0. Make sure you're in degrees on your calculator. And if that's true, well, then that means there is no work being done when the angle is 90. So both of these forces are perpendicular to the direction of motion, so they're not doing any work at all. So our initial energy is in the spring, and that's it, because the person being launched doesn't have any velocity yet, and the final energy is in the person, right? So we have all of the spring energy turning into kinetic energy. So our formula is 1/2. Sorry about the writing. This is tough to do with a mouse. 1/2 kx squared is equal to 1/2 mv squared. Okay. So let's talk real quick about constants versus variables. So K, spring constant, is something you can manipulate. We talked about that. And then X is how much you pull back the spring. That's something you can manipulate. The mass you can manipulate, and velocity changes as a result of changing one of those things. So basically what we're trying to do is say, hey, what changes as a result of something else? So I'm going to study, how does velocity change as a result of what do I want to put here? Mass, spring value, K, spring constant, or the stretch? I'm going to go with mass. Okay, so I'm going to study how mass changes how changing the mass affects the velocity. So mass is my independent variable and velocity is my dependent variable. So I'm going to set up in Desmos right now, my table. Table setup, I'm going to title my x-axis mass in kilograms and then velocity in meters per second. And now I'm going to collect some data. So let's go to lab. And I've got a certain mass in already, 115 kilograms. That's fine. Spring constant, I'm going to leave constant, right? We only have two variables. We don't want to change anything else. So I'm not going to change K. And I'm also not going to change X. I'm just going to change the mass. So right now my mass is 115. So I can type that in. And then let's go ahead and collect the velocity. Reset timer, set Trevor. And I'm always going to pull back the same amount. I'm going to keep X a constant value. I'll always go to the same X value. Fire. Start and stop. All right, 2.96 seconds to go 18 meters. So 18 divided by 2.96 is 6.08 meters per second. So I would record that right there, okay? And I'm going to do it another time. Right, you should always do multiple trials, sorry. And start. Stop. I got 2.9. I think that was the same thing as before. 18 meters divided by 2.9 seconds. Oh, I got 6.21 meters per second this time. 6.21. So let's do 3 trials for each. Go and stop. 18 seconds. Sorry, 18 meters divided by 2.92 seconds gives me 6.16 meters per second as a velocity. Okay. Now I can't see my data because I need to set my velocity values. My mass values need to change. I need to go up on mass up to about, let's say, 200. And I should be able to see some data points. All right, so we got these data points all clustered together. That's good. Now I'm going to change the mass. All right, so let's go up 125 kilograms. Pull back the exact same amount and fire. So this time it was 18 meters divided by 3.02 seconds for a speed of 5.96. 5.96 meters per second when the mass increased. And that makes sense. It's more massive, so it's harder to push, so you have less velocity. Okay? And I'm going to come back. I'm going to keep collecting data, and I'm going to pause the video, and I'll come back when I got some more data.